Let us talk about this problem. We are given a binary tree. We need to print bottom view of this binary tree. What do we mean by bottom view? If we draw vertical lines across the nodes of a binary tree, in every vertical line, whatever node comes at the bottom is part of the bottom view. And we need to consider all vertical lines from left to right. For every line, we just need to print the bottom node on this line. Now, if we see this example, we have 4 vertical lines here, one line there, and then these 2 lines. So, bottom view of this tree is 40. There's only one node in this line, we need to simply print this node. There's only one node in this line, we need to simply print in this node. We have 2 nodes in this line. So, we need to print the bottom node, right? This is top node, this is bottom node here. In this line again, we have only one node, so we need to print this one. So, here out of 10 and 50, we printed only 50. Let's see this tree. In this tree, we have these 5 vertical lines. We print 40, then 20. Then we print bottom of these 3 nodes. Now, if you see this line, we are not able to put pictorially everything into into one vertical line, and that's why we have the concept of horizontal distance to understand these vertical lines better. And the concept of horizontal distance is root's horizontal distance is 0, and left child of a node has one less horizontal distance, and right child of a node has one more horizontal distance. So left child is going to have 0 minus 1. Right child is going to have 0 plus 1. Left of this is going to have minus 1, minus 1, minus 2. This right is going to have minus 1, plus 1, 0. So these are the horizontal distances. Now whatever nodes have the same horizontal distance, they are on the same line. So there's only one node with horizontal distance minus 2. There's only one node with horizontal distance minus 1. There are 2 nodes with horizontal distance 0. So we need to print the bottom one. There's only one node at horizontal distance 1. Now we see this tree. We have 0 here. Then we have 1 minus 1. Then we have minus 2. Then we have minus 1 plus 1 0. Then on the right side we have 0 plus 1. And on the left side we have 1 minus 1 0. And on the right side we have 1 plus 1 2. We can notice that we have 3 nodes which are at horizontal distance 0. And how do we decide which of these 3 nodes should be part of bottom view? So one thing is, we are going to consider the level as a criteria. This is at level 1, this is at level 2, this is at level 3. Now we have 2 nodes at level 3. Out of these 2 nodes, which one to pick? So we always pick the nodes which are through the right child. They are considered lower than the left child when we have a tie. So we have a tie, we have 2 nodes at the same level. So we are going to consider the nodes that we are getting through the right child. We always consider the right child as bottom compared to the left child. Left is considered above. So that's why we print 60 as output. Now next thing is 30, next thing is 70. Let's see this example. In this example, we have horizontal distance is 0, then minus 1 and plus 1, then minus 1 plus 1 0, then 0 plus 1 plus 1. So we have one node at minus 1 distance, so we print it. We have 2 nodes at distance 0, 10 and 50, we print 50, bottom of these 2. We have 2 nodes at horizontal distance plus 1, so we print the bottom of these 2, which one has the lower level. So we print 60. If a tree is empty, we do not print anything. If tree has one node, we print that node. Now please pause this video and try to write down a function that takes root of a tree as an argument and prints bottom view of it. Let us now talk about the solution. The solution is based on vertical traversal. Like vertical traversal, we are going to use a map and a queue, right? And a map is going to be map in C++ and tree map in Java, which is a self-balancing binding search tree. So we are going to traverse the nodes and we are going to put their horizontal distances as keys and these nodes as values. In vertical traversal, we were putting every node for a horizontal distance in the map. Here we only need the bottom node. So what we do is, whenever we see a node for a particular horizontal distance, if there is no node for that horizontal distance in our map, we insert it. If there is a node for that horizontal distance, we override that node with the current node. And how does this overwriting work? See, we are doing tree traversal in the level order form. In vertical traversal, we were using a queue and we were traversing in the level order form. So if you're traversing in the level order form, then first you will see the top nodes of every vertical line, then bottom, then the middle nodes, and at the end you will see the bottom nodes. Since you are always overwriting the node values, at the end you will have only the nodes which are in bottom view of your given binary tree. So the first step is to construct a map. In this map, like vertical traversal, we are going to have horizontal distances as keys and nodes as values. And this map should contain bottom node for every horizontal distance. So this map is going to be a map of integer and integer. It's in vertical traversal, we were having a map where key was integer but value was a vector or array list. Here we are going to have integer as a key and integer as a value, which is the bottom node for that particular horizontal distance. Once we build this map, we simply need to traverse through the map and print the contents of it. Please note that since we are using a tree map in Java or map in C++, they are sorted containers, they are ordered containers. So if you traverse them, they are going to give you items in increasing order of keys. So you will get 40, 20, 60 and 30. Now please pause this video again and try to write down implementation yourself. Let's now see the working of the solution with a dry run on this example. So we are going to do a level order traversal, and in level order traversal, we first create a queue, then we push root into the queue. And here we are going to use a queue of pairs like we did in vertical traversal. So queue is going to have pairs and every pair is going to be node value and horizontal distance. So we first push 10 and 0 as horizontal distance for this particular node. So this is our queue initially and our map is initially empty. Now we run this standard level order traversal loop or BFS loop. Inside this loop, what we do is we extract out an item from the queue, we process it, and then we enqueue its left and right children. So we are going to extract out this item. So the value that we have now is 10 and the horizontal distance that we have is 0. After we extracted out this item, we are going to process it. So what do we mean by process here? We are going to insert it into the map, right? And we check, do we have a value already for HD? We do not have anything. So we are going to insert a value in the map with this horizontal distance. So HD and 0 is the value key and 10 is the value in the map. So this is our first entry in the map. We extracted it out, so our queue is going to become empty, and after processing this, we are going to enqueue its children. Its children are 20 and 30. So we are going to enqueue them, and when we enqueue them, we decrease the horizontal distance for the left child and we increase the horizontal distance for the right child. So we are going to have 20 minus 1 and 31. So this is what queue is going to contain at this point. Now we are again going to extract out an item, and this time we will extract out 20 and minus 1. So our value is going to be 20 and HD is going to be minus 1. Now we see, do we have an entry for minus 1 horizontal distance? We do not have it. So we are going to insert it into the map. So our map is going to contain 0, 10 and minus 1, 20. And once we have processed this, we are going to enqueue its children into the queue. So our queue is now going to contain 31, which was already there, then its children 40, and what do we put as a horizontal distance for 40? We will put minus 1, minus 2, and right child of it 50, and horizontal distance will be minus 1 plus 1, 0, 50, 0. Now we are again going to extract out an item, and this time we extract the front of this queue and we have value equal to 30 and horizontal distance is 1. Now we will check if we have this key in the map or not. We do not have, so we are going to insert it into the map. So map is going to contain 0, 10, minus 120 and a new key value pair which is 1 and 30. So this is what our map contains now. After we have inserted this into the map, we have processed this extracted out item 30 and 1. We are going to enqueue its children into the queue. And it has only one child, 60, so we'll enqueue this child into the queue. So our queue is now going to contain 40 minus 2, 50, 0 and 60, 0. Now we'll again take out an item from the queue, and this time we take out this item. So we are going to have HD as -2 and value as 40. We'll see, do we have an entry for this in the map? We do not have, so we'll insert it into the map. We do not have an entry for this horizontal distance. So we'll have 0, 10, then we'll have -120, then we'll have 130, and then we'll have -2 and 40. So this is what our map is now. And our queue will now have 50 and 60 only, because 40 has no children to process. So queue is now going to have only 50 and 60. 50, 0 and 60, 0. Now we'll again take out an item from the queue, and this time we have HD as 0 and value as 50. So what are we going to do now? We are going to look this horizontal distance in our map, and we already have an entry for horizontal distance 0. So we are going to overwrite the value 10 with new value 50, because this is a node which is at a lower level than this, right? 10 is or comes lower into vertical line, right? So we are going to overwrite this 10 with 50. So our map is now going to contain 0, 50. 50 is the new value for this key, and remaining values remain as it is, -1, 20 and 130. And we have removed 50 from the queue. So now our queue has only 60, 0. So we'll take out 60, 0 now. And when you take it out, your horizontal distance is 0 and your value is 60. So you are going to look this horizontal distance into the map. We already have an entry for this in the map. We are going to overwrite this value 50 with 60. So our map is now going to contain 0, 60, -120 and 130 and -240. So this is our final map. And since it is a tree map in Java or map in C++, it's going to store these items in sorted way. So -2 is going to be the first item that you are going to see. Now we simply traverse through the map and print all the values present in the map. So when you traverse it, you will get 40 first, because the map contains items in sorted order of keys. Then you will get 20, then you will get 60, then you will get 30. So you get the bottom view. The idea is simple. We are doing level order traversal. So the lower level items are processed later, and if you have multiple items into the same vertical line, if there is already a key present in the map, then you overwrite the value with the new lower level node that you've seen. And this is how you get the bottom view of binary. Implementation of this approach is going to be very similar to vertical traversal of binary tree. In the vertical traversal, we were making a map where integer was key and a vector or array list was a value. Vector in C++, array list in Java. Here we have even a simpler implementation. We are going to have an integer map. And whenever we see that this item is new into the map, we insert it. And if an item is already present or a horizontal distance is already present, we are going to override this value. That's the only change we are going to make from vertical order traversal.